speaker is Melih from Jagiellonian University in Cracow, and the title is Dynamical Properties Related to the Besicovitch pseudo-metric.
Thank you very much for the introduction, and I would like to thank the organizers for this opportunity. This is basically the last opportunity for me to before my test defense, so I will basically warm up for it. And if you have any question during the talk, you can just interrupt me and ask directly. Okay, as the title suggested, the main object for this talk is Besicovitch pseudometric, and we will look for how we are going to use it for in general topological dynamical systems, basically. And okay, what is it roughly speaking? Besicovitch pseudometric measures 2 points, average distance of 2 points along their orbits in space. So I will define it formally later, but this metric used to analyze statistical behaviors of generic points usually, and invariant measures related to them, and also properties like specification properties, shadowing properties, to study them, used as a tool. Yeah, that's the motivation for this talk, and I will start the talk based on 3 parts actually, but I will start in the first part, which is just the title of the first part is convergence of sequence of generic points with respect to the Besicovitch pseudometric. So, for this part, based on a preprint by Jagiellonian from Cracow, Emin, and pseudometric. We want to describe the spectrum of major theoretical dynamical systems, or let's say major theoretical dynamical systems, via behavior of the generic points. And this paper is a preprint and still needs some adjustments, but it should be on archive in 2 weeks basically. So the motivation of this paper comes from work of Lens, Spindler, and Stringer. The title of this paper is Pure Point Spectrum for Dynamical Systems, and mean Besicovitch and Dale almost 30 points. They gave
length, Daniel length, or some other?
Daniel length.
Where they are? From what university?
I don't know. I don't know. What they do, they give a characterization of discrete spectrum for ergodic measures in their papers, and we want to do something similar. We want to describe spectrum of major theoretical dynamical system in this work. Okay, before going this spectrum and generic points, I should define the main object and some basics. For us, it's a rho. This is the compact metric space. Rho is the metric on it, and we have continuous map from x to x. So basically, X is a dynamical system, topological dynamical system. For me, MT of X is the space of the invariant or probability measures. During this talk, I will only consider probability measures on the Borel sigma algebra of the X. And similarly, X is just a set of ergodic measures. We have two natural definitions for Besicovitch pseudometric. One is called dynamical Besicovitch pseudometric, one is called coordinate. One is Besicovitch pseudometric, but I will refer both of them Besicovitch pseudometric, and it will be like clear from the context which one I'm using. For a topological dynamical system XT, dynamical Besicovitch is V online. Average distances from the orbits. You can see that's why it's called dynamical, because we have
pseudo-metric different objects and this one is zero.
yeah, because of the limit superior. Basically, you can consider shift space as an example. You can have finitely many different initial coordinates, and you can have all zeros. You have two different points, but you have.
I have a stupid question. So this is obviously the arithmetic average. Could you take the geometric average of this? Does it make any sense?
I mean, if you take geometric average, I think you define another solution.
Okay.
Maybe equivalent, I don't know. I never considered it, but probably because this type of
It's just a
this
by measure and
yeah. But this type of definitions are widely used, and each of them has different names.
Yeah.
So, and coordinate-wise, for coordinate-wise, we need product space of X, which is the sequences of X where each coordinate from X and the Besicovitch symmetrical product is This one is going to be used in the second part of the talk. For the first part of the talk, I will use mainly this part, this one, the dynamical one. Now we can go to the notions related to spectrum and generic points.
So this is a pseudometric on a different space. Yeah?
Yes, on the product space. But basically, this one induces this complex.
So just if you embed x inside product space by taking orbit, then you get.
Yeah.
Okay.
Later we will do that in the second part. Okay. For the spectrum, to analyze the spectrum of mathematical system, we will consider quasi-generic points, linear generic points, and regular points, which we call something. It's a type of generic points with additional assumptions. So I should first define all of them. We say that X is generic for a invariant measurement. Along secretly increasing subsequence of n. If for all of continuous functions with a well-known definition, but sometimes it's better to define. And for me, L2 space of X and mu is the set of equivalence classes square integrable complex Fourier functions. And we have a Koopman operator on L2 space to itself. Given by F and just f of t. And for this operator, we can define eigenvalue and eigenfunctions. And it's just lambda is called eigenvalue for f. F is an eigenfunction corresponding to the lambda. Under some assumptions like lambda tends to 0, we can have 0 eigenvector. I guess you all know those kind of things. And for us, K denotes the linear span of eigenspace. Eigenspace is just unity minus and this is like eigenvalues. K is linear span of eigenfunctions. The eigenspace is basically eigenfunctions.
So you don't take the closure for K.
Yeah, I take the closure for those linear subspaces. Yes.
Who is unitary operator?
Yes. Operator. Now I can define discrete step. Okay, we say that major preserving system is stable as a inspector. If we are eigenfunctions for ut is balancing outer space. Also for S1 and for complex continuous function, we basically we denote A and F is equal to weight of X is just the averages of this one X times the Z inverse. It's the end question. And F is continuous complex value function because C is complex number from circle. X is a point in X, and we just note the averages along F times.
Is A intersect?
No, it's A n. Okay. It's A n, and it's averages till F. Yeah.
This invariant.
Yeah.
To sum of what?
F of t j of x times c to the power minus j.
Ah,
And we note is like limit of a lens obviously whenever I write this notation a of c of x, I assume sequence is convergent. There is a limit. And yeah, celebrated Vienna network states that for a major preserving system and continuous function from actually not close, I was also close. Then for almost every point x in x and proceeding as on, the limit exists.
Wait, this is for almost every, I don't know, z outside, or almost every.
Almost every x for all. Yeah.
Not all.
Yeah, and the system should be ergodic actually.
What is measure?
Measure is mean.
Measure, just find the measure.
Yeah.
Invariant.
Ergodic.
Ergodic.
Yeah. Then this limit exists for each element function for all s value from s.
Generalization of ergodic.
Yeah, kind of. If you put c
For one.
for 1, you get the ergodic value. I think I don't need for now ergodic. So.
You don't include anything about spectrum.
No, not yet.
It is just
This is just
key is one or key is
T is just a
transformation and
yeah.
we don't have any comparison.
Yeah. When I use the corner operator, I do not value it.
We also have a question from online audience. Rahami asks, is ergodicity necessary? We don't specify the value of the limit, so I would think you can just use a ergodic proposition to get existence.
Yeah. For this term, ergodicity is not necessary.
Okay.
Just as the person mentioned, we don't specify the limit yet. It's a little okay, another notion. Sorry about too many definitions, but for static terms and small linear, midterm, generic points. A point x in x is called a linear point. For later. If for continuous functions, I will consider always continuous functions because they are dancing in one. And for all proceeding as one. Sequence converges and x is a generic point. from linear term, we can say, okay, this sequence converges, but we don't know x is generic point for mu or not because we just know the existence of the limit. So for this notion, we know x is a generic point for mu. So when I say linear, it means we have a limit and it's a generic. Last two definitions before frequency. Also, this notion motivated by the paper by Lenz. They also use a similar notion. We say that the C plus 1 is a frequency for x. If there exists functions such that the slope of the absolute value of A and F is greater than 0. Last definition.
Just to clarify, if psi is the root of unity, it's always a frequency, right? Because just take constant function.
Yeah.
Constant.
Yeah. Also, if it's an eigenvalue for monopoly gradient, it will be. No. If it's a frequency, then it's in the spectrum. Actually, it's the other way around, but you will get some conditions. So, that's regular point. Let mu be T1 here. We are generic point. X is called, of course, for mu. We have all the operation on the K of the square root of 2 norm satisfy this property for frequencies of x. We have this equation. Those type of points we call regular. It's a bit technical definition, but it's necessary because using this, we will see that we can give type of spectrum. Also, these points are not like rare points in space. For ergodic measures, they have set of full measures. So,
What is this operation?
which one? K. K is the P is the projection onto K, K is the closed linear span of the eigenfunctions of unity.
And norm is just operator norm of the Hilbert space.
Yeah, it's just
So this example, if you have finite many points in your space,
then you are unit ergodic, then you are.
then
If you are finite, no.
just for example, what will happen to understand the definition? Are all points regular if you have finite space? You know?
No, if your space is unit ergodic, then all points are unit.
Ah, okay.
But I think you can have like different orbits in finite manifolds, then maybe you can, yeah.
Is this like a frequencies countable? Because you are trying
Yeah, it's like countable subset of a definition. Yes. Now, there are only variable points. Actually, this part of the paper is not in my thesis, because it is mainly written by Jagiellonian. She wrote most of those terms. So of course, we collaborated. Jagiellonian from our university. Jagiellonian. She is from India. Jagiellonian. She's another student of mine, and yeah, she showed the terror part, I showed the applications part for the Besicovitch part. I should give those errors. We have a TMI measure, and the following conditions are the measure mu is ergodic. The set of regular points and we measure the third one is there exists an regular point. So basically, if you find one point in your space which is regular, then with respect to your measure, then your measure is ergodic. Set of regular points that's ergodic. Okay, why we cared about those points? Now we can state some reasons about it.
So eigenvalues, they are frequencies, right? But to define a frequency, what about eigenvalue?
Yeah, sometimes
I guess frequencies.
frequencies is a subset of spectrum. But we will see that under some
Spectrum of point waves. Maybe spectrum.
we will see that sometimes they are equivalent notions. Assumptions. Now, actually, this is the result regarding that. Then we have a TMI measure. Is a generic point for if the set set of eigenfunctions where C is the frequency of X. If this set is an orthonormal basis for K, the closed linear span of the eigenfunctions, then mu is ergodic. And frequency of X is equivalent to spectrum of the system. This is just a lemma. I have another lemma to state there being terms.
Clarify that, for instance, is a subset of eigenvalues?
Yes. Again, we have invariant measure, X is generic point for mu, and C is the frequency for X. Then, following conditions are equivalent. Point X is regular. For mu. For continuous functions, we have E is defined. Now, using those lemmas, basically, we somehow describe spectrum for the major theoretical system. And we will now see what's the relation between Besicovitch, pseudo-metric, and those notions. Yeah.
I have a question because I still don't have a feel for this set of frequency points. So
Yeah.
take two generic points for your measure. Are the sets of frequencies the same or they can be different? For generic points, starting with generic points. Because I assume that if this is a regular point, that this is okay. if it's a regular point, are the center frequencies the same?
Yes.
Yes, I kind of assumed so. So is this true also for if you weaken the assumption to generic points?
I don't think so. You can have, for some points you can have, and for some functions you can have 0 in this limit. But for other points you may have non-zero limit.
So this is more, okay, so this is kind of like, okay.
I will define another metric here, which is called row bar on invariant measures, on space of invariant measures, which is actually a generalization of well-known metric D bar, Einstein D bar metric for shifting invariant measures. We generalized it for general topological dynamical systems, which is given by row bar. We have two invariant measures on measures of x, and lambda is a joining for invariant. We take E of this defines a metric. Actually, it is a bit hard to show this satisfied triangle inequality. And you can use Boolean lemma. This metric is stronger than mixed star metric in the sense of if you have a convergence with respect to this metric, and your measures will converge with mixed star sense. And this measure is highly related to the Besicovitch geometry when you consider general points. Lambda is joinings of and joining is just the T cross T invariant measure. You take the first marginal, you get the first measure, you take the second marginal, and you get the second measure. Yeah. I guess. Regarding relation between row bar and Besicovitch geometry. We have two invariant measures. Assume that we have increasing subsequence of natural numbers, and epsilon is suppose x in x and y are two generic points. Respectively for mu and mu. If we have limits inferior again, we take average distance along choice of 2 points, which are quasi-generic points for invariant measures, but this time we take the limiting period. And if this estimation less or equal than epsilon, then we have rho bar distance between mu and mu is less than epsilon.
You see what is in cable correct the definition of quasi-invariant, right?
Yeah. And those 2 points quasi-generic along alone. So I missed that part. Thanks. And the second part of the theorem is requires the ergodicity. So we will assume both measures are ergodic. And assume that we have 2 sets of full measures, I will denote x mu and x mu, which are subsets of generic points for the measures, and they have the full measures, just like we have it. Sets of measures. Now suppose that two metric and two measures are close in rho bar metric. Then there exists Morel sets x mu prime, subset of x mu prime, subset of x mu, such that they have full measures again. And for every x in x mu prime, there exists y in x mu prime. The Besicovitch, dynamical Besicovitch distance between 2 points are less than epsilon. So, in the first, we say, okay, we have some closeness of 2 quasi-generic points, which is similar to Besicovitch pseudo-metric estimation. If they are close enough, then the measures for those points are close enough to R. In the second, we say, okay, if the measures are close enough, then points are close in Besicovitch distance. Now, how we use those results in spec? Or spec. There. That we have a sequence of ergodic measures. Assume that there exists an ergodic measure mu in x, and such that the sequence converges to mu in rho bar metric. Then spectrum of the limit measure is just unit uniform of spectrum of which is basically everything till now that I defined, it was for this theorem. Because once we have a sequence of ergodic measures which is converging in this metric, then we have an idea of the structure of the spectrum. So, for example, for shift spaces, it is easy to construct those kind of examples which you will convert in row bar metric. Because, for example, if you take the free systems, then you will converge to Minsky measure with respect to d bar, and this metric is generalization of d bar. Then you will get the spectrum for the Minsky measure because your approximation spaces are basically periodic orbits. And yeah, how do we prove this theorem? I'm not going into details, but I will say how to do that. Assume that what we want to show. We want to show.
So is it correct to the order of intersection and union? Looks a bit weird to me. I'm missing something.
I think it's correct. Is it really for the sense? I think so. I can check it basically.
Intersection becomes smaller if n is growing. So taking union does not.
This looks like it is. Let's take the first one.
It is possible that I made some mistakes on indexes. I will just check. For me, it's just limiting rule. It looks correct. I don't know. You don't need to. Okay, it doesn't matter. This part. Let's focus on limiting theory. Okay, how to show. It means that if we have an eigenvalue which is if the C is an eigenvalue for infinite remaining values of mk's basically, then it should be eigenvalue for this. So we start with control positive, take C, which is not an eigenvalue for the system x2 mu k. Then we will show that it is not an eigenvalue for the R space. How do we show that? We take a set of regular points for each mu k, x mu k. We know that they have all sets of full measures. Then, according to UK, of course. Then we use this theorem because we know our measures are in OI. So for each sets of full measure, I will take the regular points. I will take the regular points. Then I will create for each k x mu prime k, which will have sets of full measure, and for each point there, regular point there, I can find regular point with respect to mu. Then I will take a counting intersection. I will have a set of regular points for mu, which has full measure. Then, using the lemma regarding regular points, we will see C is not the element. C is not a frequency for X, basically. Then it's not in the spectrum. It will show proof. But it's more or less in this way.
To clarify, so what does this theorem mean? Does it mean that for C to be in spectrum, it should be in spectrum of infinitely many systems responding to k?
Yeah. I mean, it should be.
Or it should be approximated by points.
It should be in the spectrum of UKs, but not finite units.
Except that
Does this cover also deeply in perception?
Sorry, I can't hear you.
Is this metric is accounted for the weekly topology? Weak topology
Yeah, this metric implies weak start topology.
is equivalent.
No, then this is stronger than weak start topology for shifting for invariant measures for a proof. And the last term regarding our spectrum. Again, X still be a topological dynamical system, and K is a strictly increasing subsequence of natural numbers. Suppose that for all n, Xm is a quasi-generic for an invariant measure mu. Along strictly increasing subsequence. If there exists a point x in x such that this limit, which we call Besicovitch pseudo-metric along the subsequence, I will write it down explicitly. Assume that we have quasi-generic points with respect to sequence of invariant measures along nk. and we have this limit, which is that we have a point, and this sequence of points generic point for different measures converging to this point.
And k is fixed, so the sequence and k is fixed for all generic points.
Yes.
Plus generic point.
Yeah.
I'm sorry, I'm missing the.
All of them quasi-generic.
So it's the same sequence.
Yes. This is the crucial part.
Here.
And the following is there exists an ergodic measure such that M converges to mu in the star topology, and X is a quasi-generic point for mu along NK. Those are the results. And limit infimum of major theoretic entropies of mu m's is greater or equal than major theoretic entropy of mu.
In this first part, we only get the mixed up convergence. We don't get the convergence in the row bar.
Actually, we can get it, but it is like you need another lemma and you need to convert a bit theorem at some technical assumptions, but it's not too important. But it is easy to write in this way. Spectrum of the limiting measure is subset of limiting infimum of spectrum measures for if mu amps as ratio of the discrete spectrum for infinity milliamps then mu has ratio without ratio discrete spectrum. And the last I don't want to write the same thing if mu has mu is totally ergodic or weakly mixing in major theoretical sense. For infinite milliamps again, then mu is totally ergodic or yeah.
Total ergodic is
One is
for
the-
ergodic for iteration.
Yes, I think
This
so,
will
but
be like the equivalent.
you can also describe it like one is the only rational number in the spectrum. 1 is the only rational number in the spectrum of the wave. And with limiting spectrum is just 1. Yeah. Yeah. That's the main result of the application part of the preference. Yeah. And again, we repeat the same idea. We take the set of regular points, then we do same approximations to get those results. Now, second part of the talk, if I have the time, which should be much more faster.
We have again question online.
Yeah.
So Spain asks, does this also apply to other spectral properties like mild mixing and strong mixing and rigidity?
Source for strong mixing, yeah. I have a proof in my thesis, but it is a bit slightly different than other proofs because those we think different data spaces and it is not applicable this method. And yeah, the other part of the talk, which is related with the classical specification and shadowing property. Both properties are well known and they basically highly related to chaotic behavior of the systems. But we will focus on the variance of those properties. And motivation for this part comes from a question by Jagiellonian and Weiss, and from their recent work. In their recent work, they prove some results related to lifting properties of generic points under the assumption of weak specification. Then they realized that, like almost 50 years ago, Kame showed similar results in his paper, but under the assumption of another variance of specification property, which is called wave specification property. And they naturally ask the question, okay, which specification property is equivalent to wave specification property or not? And to prove or disprove this, we work on this with my co-author Alexandra Treles from Jagiellonian University and other PhD students of Melih. And we showed that wave specification property is equivalent to the well-known variant of shadowing property, so-called asymptotic array shadowing property. And there are some known results which show that weak specification property implies asymptotic array shadowing property, but converge is not true in general. So we have the complete answer. Basically, we showed that weak specification implies wave specification. And for the converse, actually we also showed that two non-trivial examples. One of them is proximal, one of them is minimal, with the wave specification property, which is not possible to have those properties, those minimality or proximity, under the assumption of weak specification property. Because if you assume weak specification, then you will have several disjoint subsystems, minimal subsystems. Then minimality is already gone, and proximality also is gone because of this fact. So, yeah, basically I will state the term because definitions are too technical and I think I don't have enough time to describe all of them. And it's going to be like everything related to almost everything related to Besicovitch pseudo-metric. In each definition you will have these parts. First term, wave specification, usually by command, is equivalent to asymptotic value parallel of this weak specification with my weight specification. And converse of the curve. I will give the proximal example just by drawing. We consider shift space on binary alphabet. For us, A is just 0, 1. A to the N is product space, sequence of binary sequences. We have a shift map, and the example is just this example is actually constructed in the joint work with Michał Kupsa, Dominik Kometnat, and Jagiellonian, which we focused on the bar pseudometric, which is informally called the Besicovitch pseudometric, and we focus on the shift spaces. And but I will show you the proximal one. We will consider sequence of subshifts. I have to draw one for
It's a finite sequence.
Yeah, it's finite. I need 10 edges. So I'm trying to count right now. And it's 7 edges. And for each vertices, we have a safe symbol 0, which means we have an edge from the initial to the terminal with the label 0.
Am I going to be horrible if I ask where is V5?
Assume we have V5 here, somewhere with the same property, okay?
So it's not like it's magically disappeared, it should have been there.
Yeah. It's minus 2. We have 1, zeros, 1, zeros, 1, zeros, 1, zeros. It continues till the 8. We have only zeros till from to V8 to V9 and V9 to V0. And we also have one escaping edge from V8 to V0 with 0. And this is just for the case n equals to 1. Then we
So from V8, you go by 0 goes to V9 and V0?
yes.
I don't understand the distinction. If you have one map, it should be only one.
What you do to construct the space, you take a random vertex and you start infinite wall, and you just read the labels
Oh, I see.
along the path. Then you have a sequence, and each sequence is in which you take in space. It's a point in your space. So basically, to construct Zn, what we do from Vk to Vk plus 1 for So 0 is always possible to have it, which is safe symbol, because later we will take intersection. Without safe symbol, you can't take intersection to construct those kind of shift cases. Basically, this is this way. Yeah, this is the construction of the edges and this. Basically, for all case, you can edge with label 0. For the first 10 to the n minus 2 to the n edges, you may have 1. Then you have one escaping edges from 10 to the n minus 2 to the n plus 2 to, actually, I think this way. No, it's just visual.
Okay, so this is a way of building an infinite string or just a finite string? Infinite string.
Yeah, infinite. You start from random vertices, you take an infinite wall, and you read the labels. You have a sequence of ones and zeros. It's the point in your space.
Okay, so the length of this sequence, okay, so you build it in like periodic paths, starting from V0 and ending at V0, whatever that was. And the length of those strings can be different, can differ by 1. Am I right? Because, so in your picture, the length of this rotation starting from V0 till V0 is either 10 steps or 9 steps.
Yes.
Okay.
That's you define a periodicity, because also you need two closed paths which are ergodic.
Mm-hmm.
So to have a mixing property also. So you do this for infinitely many CNs, then you take an intersection. Then you will have your space, which is proximal, which has many nice properties as entropy dense sets of ergodic measures, as positive measure, as positive entropy. This set is hereditary shift. This space is hereditary shift, and has the weight specification property, which is actually a bit weird, because, as I told you, in proximal cases you don't have any kind of specification-like property. You don't expect that. That's why we think that the weight specification property, one of the weakest versions of the specification property. And I think for today that's all.
Questions?
I asked all my questions.
So I have a question just to understand better this metric bar. So say we have just shift two-sided infinite sequences of zeros and ones, and we have Bernoulli measures parameterized by a number p between 0 and 1. So if we have sequence pk converges to p, will the distance between the corresponding measures converge to 0?
Yes, I think it's one.
So we have Bernoulli measures.
Yeah.
Probability converging to some probability.
Yeah, it should converge.
This one is related to common factors. Because if there's no common factor, it's Cartesian product. If it is just the same, this was a 0, because we have These are zero. So for me, this clear. I need to.
There are strange results.
Mysterious.
For example, this roller metric, which is stronger than no, which is equal. It should be equal on the bar metric, Einstein d bar metric for the shift spaces. And in the joint work with Kupsa convention and Wetner, we showed that if you have, even though you have a convergence with respect to the bar metric in the metric sense, you may end up with no shift spaces, which has full support for this limit measure. Or you can have two metrics, two simplices of matrix. We have also Hausdorff distance for. We have defined Hausdorff distance for this metric, and even your simplices are close in the Hausdorff distance with respect to d bar. Your shift spaces may apart, and we construct those kind of strange examples. It's unfortunately I
Small distance. Except it says something about.
Thank you very much again.
Thank you. No questions? Let's
Smooth the czas,